Sweet. So for the benefit of the recording, hello again, everyone. My name is NRCan and I'm going to be emceeing tonight. I'm the coordinator for this project, and what that really means is I get to interact with and organize the cool people from NRCan and otherwise who are working on this project. Tonight's advisors will be Karen and Andre. Dr. Karen Smith is an associate professor at the University of Toronto. And Dr. Andre Erler is a senior climate scientist at Quanti. These two are advising all the working groups we're arranging with NRCan. The intent of tonight's session is to really get a chance to interact with the different working groups leads that we're starting, so that you have a better sense of whose objectives and whose just organization style you fit better with. Before we have announced some logistics, our working groups will follow, and how gifts and prize money will be divvied up. That said, that was a rule of thumb that we had set up. We give our working group leads really nearly full discretion in how they want to change that up. So in the presentations that they make today, and in the discussions you'll have in smaller breakout rooms later on, you really get a better sense of if it's your cup of tea. I do have one logistic announcement, and that is that unfortunately, Jan Nasinovich, who was leading the Streamflow prediction in Canadian Prairie's working group, had a personal emergency come up. And because of that, we're putting a pause on that group. We're still hopeful that that might resume in April, but more information on that soon. So because of that, tonight really we'll be having 3 working groups leads present: Forging the Future of Geological Mapping with Machine Learning, ML for Freshwater Management, and Land Cover Classification using satellite images. We might have more NRCan groups starting off in the next couple of months, but for tonight, those are the 3 groups that will be welcoming. After the leads of these groups present, we'll have small breakout rooms, and you'll have a chance to jump across multiple breakout rooms if that's your preference. You can really have a free flow discussion with the leads. For those of you who are a bit new to aggregate intellect, the way that our working groups function is less of a course format and more of a let's discuss this and figure it out together. So it's really nice to see whose personality you gel with better. After those breakout rooms, we'll then have 1 hour devoted to discussing the videos that were sent before this workshop by Dr. Karen Smith and Dr. Shane. Dr. Karen and Dr. Shane will give a really quick overview on these videos and that content, and then most of the time will really be about more of a Q&A. With that agenda given, I'm going to start off by first confirming if Dr. Hazen is in the room.
I am, yes, Amar.
Perfect. So the first group that will be quickly presenting in 3 to 5 minutes what they're about is Forging the Future of Geological Mapping with Machine Learning. It's led by Dr. Hazen Russell, project lead at Archetypal Aquifer Project and the Canada One project, Canada One Water Project. Co-leading the group with him will be Will Parkin, who's a product manager at Daily Analytics. Ladies and gentlemen, Hazen Russell and Will Parkinson.
Good day, everybody. So just a quick overview on what the objective is, a provocative title. Hopefully it caught a few people's attention. So we're going to be interested in how you can map materials using remote sense data and digital elevation models as the primary data inputs and training that. And Will can talk in a few minutes more to the mechanics of that operation. But the study area is going to be focused in northern Saskatchewan. It will consist of an approximately a 1 250,000 NTS tile. So it's near the northern edge of the northern boundary of Saskatchewan. And it has a good mix of superficial geology with some bedrock exposure And I think I explained the premise previously, but superficial geological mapping is commonly done through air photo interpretation and ground truthing. And the challenge is how to automate that and move it away from being a human-based interactive process with aerial photographs and a stereoscope. And all of the elements that are in a photograph and a stereoscope can be brought together using remote sensing data and digital elevation models. And what is missing then is the cognitive function of the interpreter. And the challenge is how to integrate the knowledge component of the human along with the data sets into a machine learning environment. And the particular challenge there is that's slightly more complicated to say than digital soils mapping is that many geological environments are paleo environments. The landscape of Canada is not necessarily representative of modern day processes. They're representative of processes in the past. And so you're trying to interpret paleo processes and environments from the modern day landscape. And Will, maybe I'll leave it there and let you introduce yourself and say a few words from the machine learning perspective.
Yeah, sure. So I'm Will Parkinson. I'm a technical product manager at Earth Daily Analytics. We're an analytics company specializing in Earth observation data. In my background, many moons ago, I worked with Hazen in grad school in this exact problem. How do we classify superficial materials in areas such as northern Canada, and how do we go about incorporating human knowledge and all the sort of implicit interpretations that humans are doing while they interpret air photos. And that is a combination of elevation profiles and then just the spectral response. In terms of the mechanics of that process, I don't know enough about the study area at the moment to comment on the specifics, but the general process is, one, you have to generate superficial material training data. And this can be a pretty onerous process depending on the nature of experts you have around. So once you get that data, then it's just a simple matter of sort of pumping that into a cloud-free multispectral image of the area, and then adding other ancillary data sources such as digital elevation models and digital elevation derivatives, which I could dive into at another time. Things like measuring the rate of change or measuring the aspect and all other sorts of other DEM derivatives. And really all that is trying to do is to capture the implicit interpretation going on by interpreters. Once you get into that classification step, this, as anyone knows in machine learning, it's sort of an endless hole depending on what you're trying to solve and the questions you're trying to get to. You could approach these types of problems in very sort of naive ways, take all the data you have and sort of cluster things in unsupervised ways and then try and do interpretation on the tail end, all the way up to very, very sophisticated sort of semantic classification models where you've split the landscape apart into these sort of statistical regions that you may use human-driven sort of heuristics and decision trees to try and classify. In some of our previous efforts in the past, we usually end up using some combination of these two approaches. So you end up generally generating a bunch of training data based on very simplistic sort of interpretations of the landscape, generating that classification, which inherently has issues with it, and then applying additional heuristics and knowledge that you have over that to make adjustments to the statistical classification. So for example, some of it would be easy, such as if you have a very clear idea of where specific superficial materials are, you could use that to mask out specific regions that you're troubling with in classifying and things like this. So you do tend to fuse a sort of combination of these highly statistical approaches with human approaches. I'll pause there and I can keep going, but I think that's probably enough to give a flavor of it.
Thank you very much, Hazen and Will. Let me just remove the spotlight for you. Dr. Zaukin, Are you in the room?
Yes. So I'm using the phone, so
Okay, that's why
yeah.
I find you. All right,
Yeah.
all right. Our next working group will be led by Dr. Zhao Lee, postdoctoral researcher at Natural Resource Canada. Her group will focus on ML for freshwater management. Ladies and gentlemen, Dr. Zhao Lee.
Yeah, thank you, Irma. So a little bit background on what we are going to do is because we know there are so many lakes in Canada, so not all the lakes are monitored with gauge. We are trying to use the satellite imagery to monitor the lakes. The methods we are going to use is to find a machine learning method to integrate multi-source satellite altimetry data. The study, we will focus on 8 lakes. We're going to randomly select them from the north to the south of Canada. The minimum program for the minimum goal for this project is to find a machine learning approach to help with the integration of multi-satellite data. And that's all about the project. If you're interested, we can discuss more in the breakout room. Thank you.
Thank you very much, Dr. Zhao. Now, the next group we have is on land cover classification using satellite images. It's led by Fraser King, PhD candidate at the University of Waterloo. Ladies and gentlemen, Fraser King.
Hello. So can you hear me all right?
Yes.
Okay. Yeah, thanks for the introduction. My group is going to be focused sort of along similar lines to what the other two have described using satellite data. We're going to be tackling, a very common problem in geospatial analysis where we're trying to do classification of different areas within on the Earth's surface. And so the basic idea is we're going to be using probably Sentinel-2, but I'll open that up to whatever satellite you think might be most suited. We're going to go over how to download data, how to sort of ingest and align it, feed it into some Python scripts, and then that's going to lead into the ML portion of the class, where we're going to use various different classifiers, looking at sport vector machines, random forests, boosted gradient models, and then potentially more complex things with some neural networks and that sort of thing, depending on your level of comfort, to see how well of a job we can do at classification. And so I think we're going to look at a few different sites across Canada. We're going to use NRCan land cover data for that at varying resolutions. And one of the big sort of takeaways, I think, with this project, for those that are already familiar with ML, is how to actually work with big data sets, because the data you get from satellites, often multispectral, you've got different bands you've got to work with, and they can be quite large depending on the study size or the study area of your project. And so we're going to learn how we can work with that properly, and sort of what detail we can tease out of that at different resolutions. So I'm interested to see what you guys come up with in terms of study areas, and I'm open to all sorts of things. So we can discuss that in more detail later, but I think it'll be really neat to sort of compare accuracy across different projects and different types of ML classification techniques. And yeah, so if you have any more questions, I guess we can chat more, but that's sort of the overview for my project.
Thank you very much, Fraser, for that quick intro. Now, in a moment, I'm going to open up open Q&A just with everyone else in the room. And after a few minutes of that, we'll start to go out in breakout rooms. Before that, I wanted to get a sense of what's the current background of folks in the room. I'll be starting a poll that asks, how much experience do you have working with data? And that could be during your boot camp, master's, PhD program, as a working professional in machine learning or otherwise. And I'm starting that poll right now. Just while that poll's happening, Dr. Karen or Dr. Andre, if you want to add on anything, now's a great time.
Yeah, I guess I could jump in. So if you haven't had a chance to check out the workshop webpage, we now have, I think, about 8 videos posted to kind of get you started. In this kind of second part of the workshop, there's also a GitHub repository that I've started to put together with different notebooks and things like that to give you some examples. Just to get you started. So the first set of videos is really very introductory, kind of more high level. These are the topics that you'll see, the jargon that you'll see. And then in the second part, we're getting into more application. So yeah, keep your eye on that space.
Thank you for sharing that, Dr. Karen. I'll just give a quick response. 38 of 43, 90% of participants have responded. 25% are between 0 to 1 years of experience. 45% are between 1 to 3. 13% are between 3 to 5. And about 20% have more than 5 years of experience in data in the room. We have quite a bit over here. All right, okay. Will we have, now we're going to begin some, so if Van Milton, yes, we will have some time for Q&A in the second hour of tonight's workshop. Okay, so before we send out people into the room, if there are any broad questions, I don't want people to get too specific just yet, any broad questions about the groups that just presented, it could be targeted to one group, or it could be targeted to all of them. You can send in your questions either on the chat or you can raise your hands. If you don't know how to raise your hands, you can unmute yourself as well. Okay, I haven't decided. Okay, so rooms will begin in a moment. Where can I learn more about derivatives? Okay, do any of the leads want to answer that?
So if you're referring to the derivatives that Will mentioned related to digital elevation models, you can join the room we're going to be in.
Okay, any expectations of minimal viable products for the projects? So what would your MVP look like, I imagine?
I think that some of those details will be discussed in the breakout groups because it will vary quite a bit, I think, from project to project. So there's no, I guess, generalization of an MVP at this time. And just to answer, I guess, one of the previous questions, if you're not sure, what group to join, you can hop around the breakout groups and just kind of see what people are chatting about. So to have that option. And we also have some web pages on the main workshop web page has some more details about the projects as well. So you can take a look at that.
Okay, someone asks, will each group do one project? Is any of the groups doing more than one project? Guess not. So every group is doing one project or maybe slight flavors of the same project.
Yeah. So it all depends a little bit on how the numbers evolve after tonight. But yeah, there will probably be several people, for each project. And so the idea is to kind of organize into smaller groups for each project, maybe maximum 3 people, and then be working on the same. All those smaller groups of 3 people within a project will be working towards the same thing. But as Fraser mentioned, there may be, he was saying it might be interesting to have different smaller groups, work on different approaches to the same problem. So this again will be sort of discussed on a project by project basis, exactly how it will all work.
Okay, now someone asks a good one. If there are 30 people choosing the same project, do all of them work together?
Right, yeah, so that I think I kind of answered that question there. So you'll kind of break up into smaller, at most 3 people per group, but there could be 30 people all working on the same project, but in your smaller groups, you'll be, because it will be hard to for you to work with more than maybe 2 other people.
I'll just quickly add on to that and say a pro tip would be that if you feel like group is too cluttered, I'd go to a different group. It often makes sense to have a sense of how much lead time you'll get. Okay, with that, I'll be opening the rooms now. So the rooms are labeled. Number 1 is geological mapping. Number 2 is freshwater management. Number 3 is land cover classification. If you don't see the option to enter the rooms, you can just shoot which room you want to join in the chat. I'll manually add you over there. Someone asks which project is more in demand. You will have to jump out to each room and figure that out. But the land cover classification one has the most registration so far.
Sorry, may I ask a general question, just for a sec?
Yeah, shoot.
Hello, everyone. I was just wondering, you've mentioned about the deadline for participating in the project. So like after tonight, well, it's the best way to decide which project you want to participate. But I have the question, like if a person decides to join later on, like for example, tomorrow I'm having a behavioral interview for a job, and obviously I won't be able to participate and involved with a lot of time, right? If the interview is successful. So I guess many people can have the same sort of situation. So if a person understands that he has spare time to participate later on, is it possible, and how the process will go on in this case?
It depends on how late is later on. If you attend this first, even if you want to attend the first 1 or 2 sessions of several groups, that's fair game, but it's better to pick a group early on just so you don't disrupt the rhythm of that group. Okay, someone wants to start the land cover classification.
I guess I'll just add to what Amar was saying there. It looks like Jan's project will be starting a bit later. So if you know that you don't have time right now or something like that, but you're interested, there's the possibility that other projects will be coming online.
Sorry, do we just ask you what to be sent to?
Yeah, go for it.
Geological mapping.
Enter geological mapping. Find geological. Same thing. If someone doesn't see the rooms, you can just ask which one you want to be sent to. Are the 6 of you here? All right. I'll be going to different breakout rooms just to make sure discussion is flowing. I'd ask you guys to do the same way. Reasonable?
Sure. Mm-hmm. Mm-hmm.
Also.
Okay. I will pause.
Basically using remote sensing data, all kinds of remote sensing.
Perfect. I hope everyone had a nice time in the relevant breakout rooms. We got to know the leads and different people who could be potentially part of their small little working group over the next 10 weeks. It's the projects really where the magic happens. Personally, I was sold on that close to a year ago. Anywho, in a moment, we're going to begin the second half of today, of this evening, where Karen is going to give a quick overview of the video she posted, and then it's going to be largely Q&A. But before we do that, we're going to do something that worked wonders in my impromptu classes back in the day. So for those of you who are comfortable, I'd ask you to open up your cameras. The next few minutes, we're going to do a few simple stretches. Now, all I want you to do is stretch the way that I'm stretching. I hope everyone can see me. Try to copy me as perfectly as you can. Oh my God. We've been at this close to an hour right now. In our impromptu classes, we had to follow the instructor exactly and then tell a story. And there were like 16 people telling 16 simultaneous stories. None of them made sense. All of them had to be impromptu. It was nuts, but it worked. It really worked. I kid you not. If you want to stand up a bit, that's fair game as well. We've been sitting for an hour. Some of you a bit more than an hour. Oh my God, these workshops. It's really nuts. Okay. Okay, I hope everyone's feeling a little bit better. Okay, so Dr. Karen, do you want to start off by a quick intro and then open up Q&A?
Sure. Yeah. So maybe I'll share my screen just to, let me see. Is it this? Yeah. Okay. I think this is the screen I want to share. I have too many things open. Can you see the web page for the web page for the workshop?
Yes, Dr. Karen, but just a quick interjection. Since some of you might not be sure how to join the working groups you just talked about in the breakout room, I just sent the link in the chat for that. Scroll down to the bottom over here. These are the 3 active working groups. Register for them and you'll automatically get an invite for session number 1.
Okay.
Okay, perfect.
All right. Okay. So I'm not going to talk too much. I want to open it up for Q&A. But I just wanted to note this is the workshop website. I'll just scroll up. You've probably seen it. And then if you scroll down, all the workshop content is here. So I'll just click on one of these as an example. There's a video posted, there's a little intro to each video, and then there are some links to give you some more resources for each video. Some of them have more links than others, but that's just to kind of give you an introduction. So we have several videos now for you to enjoy. The first is just a kind of intro to talking about, what is Earth and environmental science data. And we talk about kind of the geospatial temporal nature of this data. There's a GIS 101 introduction provided by Shane. I have 2 videos on one on numerical model data and then the uncertainties associated with that. So if you down the road end up working with numerical models. It's a bit of an intro there. And then in the part 2, which the videos are starting to show up now, we're getting into some of the Python packages. So Xarray, GeoPandas, raster.io, those kinds of things. Maybe you've seen those. And as I mentioned, there is a GitHub repo with some Jupyter notebooks to kind of work through some examples. All right, so I'll stop sharing and just open it up for questions.
Okay, you can raise your hand and Dr. Karen will get to you one by one, or you can put your questions in the chat directly.
Yeah, and I will say, if you haven't had a chance to watch any of the videos yet, well, we have another one of these sessions coming up March 31st. So there'll be more time for Q&A then as well. Quiet. That's all right.
Sorry, Dr. Karen.
Sure.
Hi, I have 2 questions.
Sure.
May come to be 3. I took a look at all the videos that we were supposed to follow up. And regarding the 4th video, talking about numerical models of the Earth and environment, where we talk about what are numerical models, what are their inputs and outputs. I found it a little bit hard. I had a hard time understanding the difference between a forecast and a projection. To some extent, they seem quite similar. And
right, yeah, I guess, well, in terms of like the equations, the underlying equations, the underlying physics of the problem, they are, very similar. We're talking about the same system if we're thinking of the atmosphere, for example. So a forecast, in order to the goal of a forecast is to make a very specific prediction about something that is going to happen at some time point in the future, and we want that to be extremely accurate, right? We want to get that forecast as perfect as possible, in order to make decisions around all sorts of things. What are you going to wear, right? What's the weather going to be? So we need excellent information on the initial conditions of our system in order to, march those equations forward in time. For a projection, what we're really interested in is kind of the general state of the system. So are we representing the system in a characteristic way? So if you think about, the current climate, for example, I could plot, a probability density function, for example, of temperature for Toronto, where I am, and it looks like it has a particular shape. When I make a climate projection for sort of the same time period, say like, the early, 2000s, I am hoping I'll get a very similar PDF, but I'm not going to be able to predict, exactly what's going to happen on a particular day, in the year 2025 or something like that. We're not setting up the problem in the same way. And this is, essentially, as I mentioned in the video, related to the fact that these systems like atmosphere, ocean are highly chaotic systems. So we just can't, we can't make a prediction very far into the future. So these problems become constrained by the boundary conditions in the system rather than the initial conditions in the system. So a boundary condition for, the climate would be something like how much solar radiation is there entering the system, how much greenhouse gases are there, how many, what is the concentration of greenhouse gases, those types of things. So those provide constraints or boundaries on how the climate can evolve, but it doesn't tell us about specifically what's going to happen on a given day. So I don't know if that clears things up.
Can I just jump
Yeah.
in a bit?
Yeah.
I think one important distinction, if you compare weather forecast to climate projection, is that for climate projections, like Karen just mentioned, you need to make a lot of assumptions about especially boundary conditions like forcing, greenhouse gas forcing, which we really don't know. We're just making assumptions here, different scenarios,
future,
right?
Yeah.
Whereas for weather forecasting, we're not really making any assumptions in this regard. Like it's not going to change much. We know that. We are really predicting the system. We're not making scenarios.
Basically, you mean that when you're doing a forecast, you are trying to make a prediction based on the conditions that you are in, but you are sort of confident in how things could evolve. Since it's just a short-term time period, you can predict, like, I know that tomorrow there isn't much to happen for this to change, so I can predict this will happen. While in projections, you are assuming different scenarios. Therefore, I could say projections render less confidence, but they're just indications, broad indications of something that we're expecting in certain conditions.
Yeah, so I would say in particular, there are in climate projections, there are assumptions that we are making which are completely outside of the domain of climate.
Right. Yeah.
Sorry, come again?
But we are making assumptions about things that are absolutely essential to the forecast and completely control the behavior, but are completely outside the realm of climate. Like we have, these are economic forecasts that the greenhouse gas concentrations are based on, right? They're not climate forecasts, but the greenhouse gas concentrations then control the climate response.
I see.
As a climate scientist, I have no idea I'm not an economist. I don't know what the greenhouse gas concentrations are going to be at 2100, right? But I have to make assumptions about it to model the climate. And this comes from a different group.
Yes, but the biggest concern that I have understanding the difference between both of them is that there was a mention, at least in the video, that the projection or the forecast is made in the short term. Yeah. And projections are made both in the short term and in the long term. So if both of them are made in the short term, wouldn't be sort of similar,
Yeah,
that's
so
why I'm trying to bring it
right.
I'm trying to take it out of.
Yeah, for the short term, the issue is more about the nature of, like, you're predicting the statistical behavior, like a distribution. Although you kind of do that for weather forecasting too. So over the short term, I don't know what really the difference is over the short term. I typically don't use the term for short term.
Yeah, I mean, so if you think about a climate model projection, you may have seen, time series. I think I showed some in the video, time series of, the evolution of global mean temperature or something like that. And we have data for that for the year 2030. We also have data for that for the year 2100. So we can make, we have data for that for the year 2023, so we can do these short-term projections as well, but that's not really usually the goal of climate modeling. But the idea is when you're running a climate model in order to do projections, you're not giving the climate model the exact initial conditions of today. If you wanted to start running the model today, you don't have to give the climate model the exact initial conditions for today. You need to give it some characteristic conditions for today in order for the model to generate a characteristic climate. But that's not the aim. We're not trying to get an accurate short-term forecast. When the aim is to get an accurate short-term forecast, the initial conditions really, really matter. You have to get those, you have to have the best data possible in order to make a reliable forecast. And this is because of this very chaotic nature of the atmosphere, the ocean. They're very sensitive to initial conditions. So if you don't give them very good initial conditions to make a weather forecast, you're not going to get a very good forecast. The forecast will deviate in some way. That's, again, it will be characteristic deviation. It won't be unphysical, but it won't be accurate. So I don't know. These are.
Yeah, in general, I would say, like, historically, there was a clear distinction between the weather prediction and climate projection, but we're really moving into a realm where there's a seamless transition. There is probabilistic seasonal forecasting. That people are working on decadal forecasting now, which is so similar to climate projection from a technical perspective, but and also from an interpretation point of view, it gets more like that. So it's don't worry too much about the clear distinction between that. There is at this point, there's a continuum or a spectrum of different types of forecasts. Weather prediction over short term and climate projection over the long term are the two extreme ends of that spectrum.
Yeah. Yeah, one way of, if we see things that way, it's easier to make a distinction between both,
Yeah. So the reason why we use projection is just to make this distinction that people don't think it's the same as a weather forecast, because there are some differences. But yeah, it's a continuum.
Okay. Yeah, and the model that you use to do those two things could be the same model, right? It's just
right.
So as I was, what I was really trying to highlight in the video was that the data that are important for those problems are different, right? So for a forecast, data on initial conditions that primarily, come from satellites are really, really important versus a climate projection where the data that are important to be able to set up those type of simulations is different.
Okay, so there was another thing that even I think it's Mr. Sopan has been mentioning in the chat. It talks about a boundary. There are two concepts that you mentioned in the video. This was in video number 5 when you talk about uncertainties. You talk about anomalies, and also you mentioned about the boundary problem. What do you mean exactly by boundary? Because when you think of boundary, we talk about some mean of limiting, of defining a certain scope, whether it's a specific environmental factor, or is a specific space, or is a time frame, or whatever.
Yeah,
but
so
this is at least how I understand it.
Yeah.
But how would I differentiate a boundary problem from a initial value problem?
Right. So this is basically what we've just been talking about. So an initial value problem or initial condition problem is something like a forecast, where you really need to know the initial conditions of your system. You need to know that data really well in order to make a reasonable forecast. The boundary value or boundary condition problem is more like a projection. So yeah, I have a link. I don't know if you had a chance to look at it, but there's a link, a really nice blog post by Steve Easterbrook that kind of goes into some more detail on this differentiation between initial condition and boundary condition, or initial value or boundary value. These are the same things. These two types of problems. So maybe take a look at that. This is, in terms of the types of projects that we'll be working on for the working groups, this is probably not necessarily, these details are maybe not necessarily key, but it's just kind of an important distinction. If you're working with forecast data versus working with model data, sometime in the future, kind of understanding how these problems are set up and what they're just, what the aim is, and the data to generate these are kind of important to know. So I just made a quick video about those. Yes, yes. So solar radiation would be an example of a boundary condition. So if your system, if you define your system as the Earth, the Earth's atmosphere, what is something that you need to know at the boundary of that system? You need to know the solar radiation. The greenhouse gas concentrations are also boundary condition, something like that. Humidity, yeah, could be an initial condition, you know, temperature, surface pressure, these very, very specific, the state of the atmosphere would be an initial condition. Yeah. Yeah.
Thank you very much.
Sure.
Just the last question that I asked.
Sorry, I was just going to interrupt and see, you know, if we want to see if anyone else has a question, and then we can come back to some of your questions just to kind of give everyone a chance. But let's see, maybe there's no other questions.
I have a question, Professor Smith. Does simulation in the Earth's environment totally validated or not? Because when we do simulation in engineering problems, we validate the simulation. But for the environment, I don't know if.
Yeah, great question. So of course we do that as best that we can, right? So we have all of these Earth observing satellites, you know, weather stations, you know, all sorts of data, and we validate our simulations, you know, as best we can based on the observational data sets that we have. And certainly like weather forecasts are, you know, there's always scrutiny of, you know, why did this forecast not, you know, why did we mess up this forecast? We could, you know, there's lots of validation that goes on with weather forecasting systems. Climate models, it's a little bit different because we're not necessarily trying to get a perfect forecast or something like that. We're trying to get the statistics of the system right. But yeah, these models, they have biases, you know, just like any model. They're not perfect representations of the climate system, which is a huge system to try to model. But they do, you know, a reasonable job. Yeah. So certainly in the model development process, validation is a big part of it.
But it's often limited by the availability of observational data, especially direct in situ data, so weather stations or weather balloons, or also extreme gauges or groundwater observation wells. These are very sparse, and because they're expensive to operate, especially in remote regions. Satellite data is much more widely available, but it gives it only gives you one perspective, and that's from above, right? So.
Yeah, and I guess to add on to that, you can't really observe the ocean very well by satellite. You can observe the, you know, the surface, but that is one, you know, region of the climate system that is difficult to observe. You know, so we have all these autonomous floats going around, these Argo floats and different ship transects and all sorts of ways that we try to take observations of the ocean, but it's certainly not as well observed as the atmosphere is.
Yeah, and the other thing is that you need a long time series of observations, and that basically you're relying on somebody having had the foresight to take observations 30 years ago. We would only really benefit from the observations that we take now in a couple of decades, and this is always a hard sell for politicians, right? So
yeah, that's true. All right. There's a question in the chat about uncertainty. So uncertainty in numerical models, is that the question, or about different sort of machine learning models or yes, machine learning models. Right. Yeah, that's a great question. So that would maybe be a question more for the project leads, but I think Fraser did mention for his project, for example, something about, yeah, comparing different methods. So that's certainly a good approach. In the climate modeling world with numerical models, we do that all the time. We compare different models to see to what extent they agree or differ. So Henry, if you go to the workshop website and scroll down, there are working group links, and each working group has a registration button, so you can sign up. Any other questions? Maybe we can circle back to Hamilton. Did you have another question?
Yes, was just something that I missed in your today's presentation. I think, was it today, or I can't really recall, when you were talking about I think it was in video 5 probably. In those scenarios, you mentioned something, the definition of anomaly. You were talking about
okay.
temperature anomalies.
Yeah. So the way anomaly is defined, at least for climate, and these can, I think this word is kind of a jargon word sometimes, right? So at least in the plot that I was showing in video 5, it's really just you pick some reference time period. So let's say globally average temperature averaged over a 30-year period from 1951 to 1980 or something. That's often a common reference period. And then all the temperatures, the annual temperatures, you subtract that reference period, and you just get a deviation or an anomaly with respect to that particular reference period. So I think in the time series plot I showed in video 5, they had 2 different anomalies on the both y-axes. They picked 2 different reference periods and calculated their anomaly in these 2 different ways. So it's really just kind of a deviation from some baseline temperature that's been kind of agreed on in the community as being, for climate, it's kind of a time period where the influence of anthropogenic climate change is pretty small. So we kind of use that as kind of a baseline.
Okay. Now it makes sense. Yeah, thank you.
So there's some chatting going on here. Andre, do you want to jump in with what you guys are chatting about?
Yeah. So the question was about to which extent machine learning improves over current benchmark models, and that depends a lot which area you're looking at. So in remote sensing, actually, some form of machine learning has been used for quite a while. Like land classification is not that uncommon to use machine learning. It's just that the techniques that are being used are getting more complex. So like decision trees or like random forests have been used for a long time. So in hydrological modeling, recently there has been some significant advance with LSTMs. In climate modeling, it really depends again what you're looking at. So there has been some progress in sort of short-term rain prediction, sort of essentially like a frame prediction on a radar image. But this is very specific, and this is really very short-term. So over like 3 hours or something. For climate modeling itself, well, there are emulator models, but and that has been around for a while, but then there's not really anything you can compare them to except maybe like a linear regression or something. Because that's really purely machine learning, or it's purely statistical problem, right? Downscaling, again, it's kind of a machine learning problem to begin with, and then what you compare it to is sort of like simple methods, like essentially, well, quantile mapping is probably the most sophisticated. That's not explicitly machine learning, and there, I'm not sure if Karen, are you aware of any papers that and they also haven't really applied that in large scale to climate models, really, just sort of some proof of concept. So in climate modeling, I'd say there's a lot of sort of proof of concept where they've taken one little aspect of atmospheric modeling and thrown in some machine learning technique at it, and it worked. But for the whole,
Oops.
Oh no.
Can anyone hear Andre?
No.
No.
The
Andre.
audio disappeared.
Oh, and he's frozen.
Oh, and it, yeah.
Can you hear us? Andre is
He's frozen.
Oh, I
gone.
think we lost him. Anyway, so we will jump to the next question in the chat. So I think this is the next question.
whole thing, like a climate.
Whoop.
Okay, so it seems I just got disconnected.
Yeah, we missed about a minute of what you were saying there.
Okay. Yeah, I mean, I can just stop here. Yeah, in climate modeling, different aspects of models have been successfully simulated with or replaced with machine learning, but not the whole climate model.
Yeah. So there's a question about where do you find papers on machine learning? So there are, I think, what Andre's referring to are, peer-reviewed journal articles, and there are different journals actually specifically related to machine learning in geoscience that are starting to come out. Otherwise, these papers would be scattered in existing like domain specific research journals, not in a dedicated journal, but that's starting to change. So stay tuned. There'll be some dedicated journals coming out soon.
Yeah, but mostly it's in domain specific journals. Some of them are open access though. And we can probably, if you're interested in a specific discipline, we could probably give you a pointer.
Yeah, and there's a like a preprint website called Earth Archive, and so some of these papers may be there as well, kind of posted. So a question about projects. Personally, I'm interested in topics related to meteorology, atmospheric science. Is there a possibility to open a project on topic related to meteorology? Possibly in the future. I have a couple of projects in mind as well, but at the moment I'm still teaching, and it's still the semester, and I don't have this bandwidth to put a project together, but maybe in the future that's something we could think about if people are interested. But not at the moment.
Yes, sorry, just I'll quickly interject there. If you are interested in starting a group like that yourself, you can drop me a message, Amar Khan, on Slack. I can help arrange an advisor for you, maybe put something together.
There we go. Yeah, let's crowdsource this project. So Shane also mentioned another link where there could be some papers that are publicly available. And Medium, there are lots of cool blog posts on Medium about geoscience related machine learning and machine learning problems. So you can kind of check that out as well. Oh, if I were going to participate in one of the projects, which one would I choose? Well, my choice would probably not be data science related. It would probably be more topic specific. So I don't know if I necessarily have the best advice if you're, in this to learn about machine learning, but they're all related in a way, right? Trying to, use remote sensing data. So in terms of familiarizing yourself with that type of data, then they all are sort of have some similarities.
So I would also point out so we may have another project that would be about Streamflow Forecasting. That's Jan's project, who unfortunately couldn't be here today. And so that one would probably be the most climate related, if you want, if you are really interested in working with weather prediction data or climate data, because as we talked previously about boundary conditions for streamflow prediction, of course, weather is the dominant boundary condition. And yeah, so if you're interested in that, this is probably a project that, well, it still has a high likelihood of happening, I'd say. And this is also something where I could advise if somebody else wanted to take over the leadership of that, if Jan really can't make it. And also for other projects. So the main reason that most of the projects are remote sensing focused is that this is sponsored by NRCan, and NRCan primarily does sort of land cover and natural resources and doesn't do climate modeling. Mm-hmm. That's really the main reason. If you are interested in working on climate modeling, talk to Karen or myself. We are atmospheric scientists and we have lots of ideas, but we may not have time at the moment.
Yeah. So we're
sorry to hear you have no time.
Well, we have time for this, but it's just a busy time in the academic year, but there's potentially time in the summer. So so questions about data. Satellite image data, can we include outside data from drone imaging? So I think the idea with these projects is to use, publicly available data if there is, that everyone can work with. If there is other data out there that's publicly available that is complementary, yeah, go for it. Yeah, so Shane's posted some other resources, great. And a question about meetup. So each group has kind of their own meeting time. If you check out the links on the workshop website, it usually has some information about the meetup times. So check that out.
I had a question for you, Karen.
Mm-hmm.
What's going to happen in the third and final workshop we'll be hosting on the 31st of March?
Yeah, so so the idea for that workshop is like live Q&A session is to have actually some guest speakers come. So we'll have a presentation from one of my colleagues at University of Toronto Scarborough, who thinks a lot about data visualization and accessibility around data visualization. And he's a geophysicist. So he's going to give a presentation about that. And then I'm hoping that Andre will give a presentation about some of the stuff that that Aquanti does, and the type of, just to give you a bit of more flavor about the applications of this type of machine learning. And Shane as well, who's here, he is putting together a presentation about his own research. So both of these projects, or both of the Andre and Shane's presentations, will be more in the kind of earth science realm, whereas I have my kind of climate science bias that it trickles into all of the videos and that sort of thing. So you'll get a bit of a flavor of, you know, what's going on in the applications. And then, of course, more Q&A. There'll be more videos and notebooks kind of appearing. So I'll be here to answer questions as well. Any other questions?
All right.
Yeah, if you happen to have a burning question, you know, between now and the next live Q&A, you can, you know, use Slack and reach out and, you know, ask the group, or and I check in every day to see what's going on. So yeah.
All right. Okay. We're going to move on now towards the conclusion. Someone has asked for the Slack link that was sent in the follow-up email to session number 1. I'll also resend that here right now. Strongly encourage joining the DG Environmental Data Science Slack channel for those of you who already haven't. It'll be mentioned again in the follow-up email to this. I love giving tons of reminders. Now, what's next is what many of you are thinking. And really after this, we're going to shift gears more towards doing stuff. In the next couple of days, the working groups are about to begin. And you'll see that the first few sessions will probably be about setting up your data, getting in sync with the rest of your team, having a sense of where I want to go. And I strongly encourage everyone to be especially diligent in the first 3 sessions of your workshop. I do a fair bit of statistics on this, and we found that those who stick around for the first 3 sessions have the best chances of continuing on. During those sessions, you'll also be asked that as you're solving problems, you share them to the rest of the group in a specific format. All of those details will be mentioned in session number 1 for you. I imagine most of you have already registered. For those of you who have not, yes, keep an eye out on the follow-up email. You can attend several working groups for the first 1 or 2 sessions if you like, if you're still a bit unsure. But then after that, you should pick one and stick to it. Unless you're not working full-time, in that case, go nuts. With that, does Andre, Karen, or any of the working group leads want to say anything before we call it?
Just thanks for coming out, and really excited to get the working groups going, and yeah, looking forward to seeing you back here on the 31st.
Perfect.
Thanks, guys.
Take care, guys. See you not this upcoming Thursday, but the Thursday after that on the 31st. Take care. Have a good night.
Bye, everyone.
Don't worry, there'll be a recording for that session as well. Yes.